An apple, earth, and a wet ball. Gravity investigated. If we have two masses, their gravity will pull them towards each other. And together they can act onto a third mass. Multiple small masses close together can work like one bigger mass. Their gravity adds up. Every small body, large body, or whole systems of different masses have a common center of mass. Outside objects will be drawn towards this center. Mathematically, gravity is described by the universal law of gravity. It states that the force equals a constant g times the product of mass 1 and mass 2 divided by the distance between them squared. G is a very small number, and this makes gravity itself a very weak force. It takes big masses in short distances to get a big gravitational force. Let's play around a bit. First, the masses. Bigger masses mean bigger gravity. Smaller masses, smaller gravity. Now the distance. Bigger distance, smaller gravity. Smaller distance, bigger gravity. Simple, isn't it?
Can we find out how fast an apple falls down?
Sure we can. We just need two masses, your apple and Earth. Let's assume you drop your apple near Earth's surface. So the distance between apple and the center of Earth is roughly equal to Earth's radius. Earth is so big that a few meters won't affect our calculation that much. If you want to accelerate a mass, your apple for instance, you need a force. This is what Newton's first law says. Force equals mass times acceleration. You can test this yourself. It takes less force to push this truck than this truck. But in your case, it's the apple moving. But let's get back to the universal law of gravity to find out more about that force onto your apple. We just have to put in the right names. Since gravity is the force that acts onto your apple, we have to combine these two laws. The force on the right side is the same as the force on the left. When you look closely at that equation, you will notice something interesting. The mass of our apple appears on both sides and it cancels out. So we don't need the mass of the apple at all to find out how it will be accelerated. Even better, you can drop an apple or an Opel, it doesn't matter. They both fall down with the same acceleration. The only mass that stays in the equation is the mass of our Earth. And yes, some guys did test this.
Oh, come on!
Let's tidy up a bit. Now that the equation looks much simpler, we can look up the needed values and plug them in. The calculator tells us the acceleration is about 9.81 meters per second squared. That means that each second the apple gains 9.81 meters per second more speed. Or the Opel.
Okay, but how about the moon?
Moon and Earth attract each other gravitationally. But the moon does not fall down like the apple, because it orbits our Earth. For this orbit to be stable, we need a force that balances out the gravitational pull. This force is a centrifugal force, caused by inertia. When we set gravitational force equal to centrifugal force, as in a stable orbit, we can calculate the speed of the Moon in its orbit. On the left side, the side of the gravity, we put in the universal law of gravity that we've seen earlier. And on the right side, we put in the formula for the centrifugal force. Because both forces balance each other out, we can set them equal. And again, we see that certain values appear on both sides and cancel each other. The mass of the Moon and the Earth-Moon distance. Let's take them away and simplify the equation. Because v, the velocity of the Moon in its orbit, is still squared, we need to take the square root on both sides. Now we look up the values, plug them in, and find the velocity of the Moon, 1018.3 meters per second. Okay, but how long does it take the Moon for a full circle? We take the distance between Earth and Moon and put it into the equation for the circumference of a circle. We find out that one full circle has a length of about 2.4 billion meters. When we divide that by the Moon's velocity, we get the time it takes the Moon to do a full circle in seconds. This is an impressive number, but it amounts to 27.4 days. And that is almost exactly what we observe. We used the same law of gravity for the apple and for the Moon, and in both cases got the right result. Even more, by cancellation we found out that it does not matter if we let an apple fall down or an Opel. Similarly, it does not matter if it is the Moon or any other thing orbiting the Earth. As long as it is 384,000 kilometers away, it will take about 27.4 days for a stable orbit, be it a Moon or a man. Eric D. from T wants to know, why should water stick to a spinning Earth but not to a spinning tennis ball? Good question, Eric. Let's try to find it out. When we see the water and the ball or Earth as two masses, we can use the same laws as in the Earth-Moon example. The water kind of orbits around the center of mass of the ball or Earth. If we neglect electromagnetism for this moment, we again have two forces to think about. Gravity pulling the water inwards and centrifugal force pushing it away. In order to lose the water, centrifugal force has to be bigger than gravity. We look up the equations for gravity and centrifugal force and put in the values for the tennis ball first. With the help of a calculator, we find that the gravitational force between 10 grams of water and a tennis ball would be 2.94 times 10 to the power of minus 11. This is very, very small. If we do the same calculation for the water on our planet, we get 1.357 times 10 to the power of 19. Again, comparing those numbers, you can easily see why it doesn't work just to scale down gravitational systems. But we wanted to know how fast they can spin before they're spreading their water into space. So let's look on the right side of the equation, the side of the centrifugal force. We set it equal to gravity, put in the values and see what comes out. the result. If there were no other forces except gravity and centrifugal force, Earth could spin 17.5 times faster than today before it loses its water. And the tennis ball would need a surface spinning velocity of 0.01 millimeters per second. In other words, Earth could spin 17.5 times in 24 hours, but the tennis ball only 4 times in 24 hours. And I want to say it again, we totally ignored the electromagnetic forces that, especially in the tennis ball, will be hugely stronger than gravity. And here is another question from Eric D. from T. How is it that gravity is so strong that it can hold all the oceans, buildings and people stuck to the underside of the ball Earth, but so weak that it allows birds, bugs, smoke and balloons to casually evade its grips completely? Another good question, Eric. Let's see about that. First of all, birds have to flap their wings in order to stay in the sky. If they don't, gravity pulls them down. So anything that wants to stay up in the air has to work against gravity and apply a counterforce. This force can come from a lot of different sources. For instance, air pressure differences on an airplane wing, chemical energy turned into momentum like in cannons or rockets, or magnetism. The bigger the mass you want to lift up, the stronger the force you need to overcome gravity. So, how strong has this force to be in reality? We can calculate it with the same law of universal gravity that we used for the apple, the moon and the spinning tennis ball. I will spare you the math this time and just give you the results. A small house needs about 2 million newtons to lift off. A butterfly only 0.05 newtons. So Eric D. from T, who do you think can fly better? Perhaps one last word to Eric D. from T. When we use words like up and down, we usually mean away from Earth or towards Earth. Remember, masses have a center, and so has Earth. Other masses get attracted towards it, no matter from which direction. So up and down only have a local meaning. There is no underside to our planet.